And so when we did chapter 2, it was just rules of differentiation. So we're just talking about calculus and just differentiating functions. So we started with first principles. We began this in late year 11 and we continued it in year 12. I've got a nice easy one that we're going to start with here. And all we're going to do today is just pop in and out of each exercise in chapter 2. Just choose a few problems from each and do them together. And then it'll be an opportunity for you to look back at your test and ask me questions and direct your efforts where you feel the need. So first principles. This is how we come about the slope function using the first principles formula. So we have f of x plus h, take f of x on top of h. So what we need to do, if we want to find f dash of x, we need to make the statement, it's the limit as h approaches 0 of f of x plus h. So that's where we substitute x plus h into this equation. Okay, so there's my f of x plus h. Take away f of x, all on top of h. So we know these first principles ones, we're pretty familiar with them. It's just that methodological process, isn't it? It's expand, collect like terms, factorise h, cancel h, apply the limits. Always the same. Let's do it. Now, often this is one thing I've said before, often there's a temptation to expand and collect like terms in one step. You're thinking, I'm going to be efficient here, let's try and save some time. But that also increases the probability of making an error. So when I'm doing it, it's very easy to make a simple error on these things, isn't it? You know, you just miss a negative somewhere or don't have a bracket somewhere, and it stuffs up the whole thing. So let's keep going here. We're looking for like terms. We're going to have x squared take x squared, that will cancel. We're going to have minus 3x take minus 3x, that will cancel, and then 4 take 4. And so every term we're left with, we know we're on the right track, if every term that we have left over has a h in it. We've got 2xh plus h squared, take 3h on top of h. Factorise and cancel h. So that's going to be I'll apply the limit in that step as well. And we know this is true because we can use simple differentiation. We get 2x take 3. 2x take 3. Okay. Those principles, they're fun. Every exam for the past 20 years has had at least one first principles problem. There's a couple that have 2. So there's going to be one in there. And it'll probably be a bit harder than this one. This is a nice easy one that you get into year 11. But just get you to think about the ideas around it. Very good. Okay, let's move on to simple differentiation, which I've got up here. We've got exercise 2b. And for us to differentiate using simple differentiation, we need to first express everything at the top of the fraction as x to the power of n, and then it's ready to differentiate. So before we can differentiate here, we need to change that. So this is going to be 3x squared plus 4x, take 5x to the minus 1 plus 2. So using index laws to bring it to the top. I can wait a bit, sorry. I'm going to be quick. Some people are still writing down the lines. Just excited. Okay, so we express everything as x to the n. Look, that's still the same function, okay? We haven't done anything to it. And then bam, let's differentiate dy and dx. So we've gone y, we're ready to differentiate. Let's do it. 6x plus 4, take. Sorry, drops off. Okay, now I can tell you the first page of the exam, again, for the past 20 years, there's always been differentiate the following without simplifying. Okay? Yeah. occasionally they'll throw in and integrate the following, perform the following indefinite interval. So there'll be a question like this, or there's a product rule, something like that. Always on the first page. Get the brain juices flowing. Okay, when we're confronted with a problem like this, we want to split the denominator. So what that means is we're still going to have f of x. We're not changing it yet. That's going to be x squared on x plus 6 on x. So you can think about that's a legitimate operation, because that's like going, if we have 3 on 4 plus 2 on 4. Okay, if we think of that as a fraction operation, well, they have the same denominator, which means we can collect them. So that's going to be 3 plus 2 on top of 4, or 5 on top of 4. Okay, that's okay. That's all good fraction operations. So all we're doing is the reverse. We're starting with this statement and going back the other way. And what that allows us to do is we can now simplify these using index laws. We have x plus 6x to the minus 1, and then we differentiate. Now some people, particularly year 11s when they're first beginning this, they'll just write equals, 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 equals. Okay, we don't need that, we need to be very clear. This is f of x, this is f of x, and f dash of x. Okay, this is where we're performing the differentiation step. Okay, so that's enough of 2b, I reckon. Let's jump into 2c. Now in 2c we did the chain rule. So, the chain rule is if we have y equals f of x to the power of n, then dy on dx is n f of x, n take 1. Okay, so let's do I'll just make one up here, a reasonably tricky one. Let's go with 3 on top of the square root of x squared take 5x. Okay. So we need to somehow express it like this, f of x to the power of n. So we could write it as 3 times x squared take 5x to the power of minus half. Okay, square root means it's the power of a half, it's at the bottom. So when we bring it to the top, it becomes negative half. That 3 is just going to hang out, and you can see the resemblance. There's f of x. Excuse me, I'm missing something there. That's better. There's f of x, there's the n, we're ready to differentiate. Okay, everybody ready? So then we'll go, well that's y, that's the same function. Here's dy on dx. The 3 is just hanging out. Okay, the 3 staying there, and then we go, f of x then, it goes n, f of x, n take 1. So that's minus half, f of x to the n take 1. So n, f of x, n take 1. And then times by f dash of x, times by the derivative of what's inside here, 2x take 5. Okay. Now I've said, first question always says, differentiate without simplifying, and 95% of the differentiation is like that. Occasionally it says show that the derivative is this, in which case you do need to manipulate it towards something, don't you? So what are some ways that you could simplify this if it does want you to direct it in a certain direction? Let's think of this. Well, that's just going to be minus 3 on 2 out the front. 2x take 5 is just hanging out the top. And then at the bottom, you have this to the negative 3 on 2. And we know that a to the negative half is 1 on root a. And a to the negative 3 on 2 is 1 on a root a. So one way that they could write that, if they wanted to simplify it, would be x squared take 5x times the square root of x squared take 5x. Okay, a root a. And then we've accounted for everything. Okay, you could distribute the 3, you could distribute the 2. Cool. So chain rule, okay with the chain rule? You want to do another one? If one person wants to do another one, do another one. If people are happy to move on.
Yeah, let's do another one.
Let's do another one. Thank you, Captain. So let's do rules. Let's do 5 on top of 2x take x to the 4 to the power of 3. Okay, step 1, express it at the top of the fraction. So we can see f of x to the power of n. Okay, let's differentiate. 5's just hanging out. We have n, f of x, n take 1, times f dash of x. Cool. So if you're worried about the chain rule, remind yourself towards the end of the lesson we can revise some of 2c. Next we have the product rule and the quotient rule, and I'm going to sort of combine them with exponentials and logarithmic functions as well.
I'm sorry, Mr. Woods, do we have to simplify that any further?
No, unless it says show that it rearranges to this. So, yeah, good question. Cool. So I'm just going to write the product rule up here. And the quotient rule. So the product rule is if we have u times v, then it's u dash v plus u v dash. And the quotient rule okay, so there's the product rule and the quotient rule. Also, I want to remind you if we have, let's go function and derivative. So let's make a bit of a table here. Okay, if we have e to the x, the derivative is e to the x. Function and table, function and derivative. Okay, if we have e to the f of x, the derivative is f dash of x, e to the f of x. And if we have ln of x, the derivative is 1 on x. And if we have ln of f of x, the derivative is f dash of x on top of f of x. Okay, so there's a bit of a table for us to do the product rule, the quotient rule, exponentials and logarithms all in one go. So I'm going to come up with a few problems.
Is that on the formula? Will that be on the formula sheet?
I can bring it up in a moment. This is.
Yeah.
I don't think these are.
Okay.
Yeah. Let them have a look at it. Okay, so let's do a couple of examples. Let's do y equals, and then let's do f of x equals. Okay, so in the first one, I'm looking at that, I'm seeing x squared e to the 5x take 1. I'm going, that's x squared times e to the 5x take 1. That's going to be a product rule. So we've got to identify u, identify v. So u is x squared, v is e to the 5x take 1. And then we differentiate each term respectively. X squared is 2x, v dash. So if we have e to the f of x, e to the f of x, the derivative is f dash of x, e to the f of x. So the derivative of 5x take 1 is 5, e to the 5x take 1. Smash it together. U dash v. So let's make the statement. This is y, here's our working, here's the derivative. U dash v plus u v dash. Okay, quotient rule. We've got one function divided by another function, so we know we're using the quotient rule. U is ln x. The derivative of ln x is 1 on x.
Would that be take 3 on 2? Oh, no, never mind, sorry.
Yeah, good question. No, we're not moving it to the top, we're leaving it at the bottom. Yep. So that's f of x, so here's f dash of x. So just make sure you use brackets. We could simplify that one a bit. We'll leave it, I think. Okay, how are we feeling about those? They're not too bad. Product rule, quotient rule. So, let's continue with this one actually, because this might be a teachable moment. I should jump on it. So remember how they present you with these things, and then they say stuff like, find where the slope is horizontal. Okay, so this is a function, right? And they want to know when the slope is horizontal. So if it's got a horizontal slope, you can think of a function. Horizontal slope means the slope is 0, doesn't it? So it wants us to find where the slope is 0. When we're differentiating, when we're performing this process, this is the slope function. And so what that means is for any value of x, it can tell you how steep the function is. So if we're asked to find when is the slope horizontal or when is the slope equal to 2, all we're going to do is make that function equal to the slope it's asking about. This is the slope function, and it says when is the slope horizontal? Horizontal means a slope of 0. Okay? If we're going to solve a problem like this, we're going to want to factorise what we can, and then try and solve it. So looking at these key terms, definitely x is common, and this e to the 5x take 1 is common as well. So I'm going to rip that out the front. So we're going to have x e to the 5x take 1 out the front, and in brackets we're going to be left with 2 plus 5x being equal to 0. Okay? And then we are going to apply the null factor law. Alright? So we've got 3 solutions here, right? Either x is 0, e to the 5x take 1 is 0, or 2 plus 5x is 0. Okay, there are 3 solutions. This one we don't need to process any further, that's fine. How about this one? No solution to an exponential being equal to 0 is there. Okay, an exponential will never equal 0. No solution. That goes for anything. E, 2, 5, doesn't matter the number, never equals 0. And then 2 plus 5x is 0. This is a nice linear equation to solve. We've got 5x is minus 2, x is minus 2/5. So we have the function is horizontal. It has a slope of 0 at x is 0 and at x is minus 2 and 5. Okay? Say it wanted you to find the coordinates where it's horizontal. You've got the x coordinates. If we need to find the y coordinates, how are we going to do that? We plug it back into the original function. Okay, we take those x values, plug them into the original function. So if you put x is 0 in there, the y value is going to be 0. 0 times that will be 0. So one of the points where it has horizontal slope is 0, 0.
When you found the x values, why are you doing that? Like,
why am I finding these x values? Yeah, so I'm saying one question that you've seen in this unit, in this topic we've done, is it says find the coordinates when the slope is horizontal. Well, the slope is horizontal when the derivative function equals 0.
How'd you find that x equals 0?
So here, I'm applying the null factor law there. Null factor law doesn't just have to be for 2 terms, like you can be for 3, 4. Product of anything equals 0, it means one of them has to be 0. Because there's no set of non-zero numbers that you can multiply to get 0. So one of them has to be 0, is what it's saying. Okay, so then we can look at, if we're happy with the product law, quotient rule, and e's and ln's, we can look at trig, and we can look at second derivatives. Okay, and that'll be the unit. So I'll clear the board space. I'll leave quotient rule and product rule up, and I might draw another table up here for sine and cos. So if we have sine goes to cos, cos goes to negative sine, tan goes to 1 on cos squared. Okay, and then if we have sine of f of x, f dash of x, cos of f of x. If we have cos of f of x goes to minus f dash of x, sine of f of x. I can't remember this one, I'll have to check. You can find it in the notes there. Okay, is anyone still writing this down?
That's right, I've got it. Yeah. You can rub it out. Yeah.
Okay, we'll just do one problem here, I think. Find the second derivative. So that just means you just have to differentiate twice, doesn't it? Given sine of f of x here. Okay, so let's look at how we're going to differentiate sine of f of x. That's this one here. It's going to go to f dash of x cos of f of x. So this one, f dash of x in one go, we can do it. It's going to be 2x plus 3. Okay, the derivative of that times by cos of f of x. Okay, so that's our f dash of x. Okay, then we're ready to find f double dash of x. What rule do we think we might be using? If I'm looking at this function and I want to differentiate it, what can we see?
Product rule.
Excellent, it does it. Genius, 2x plus 3, and cos of x squared plus 3x. Okay, so u dash is going to be 2, v dash will be double dash. Just like that. Q. So that's pretty well all the content that we all the laws and a bit of exposure to the stuff we needed for chapter 2. First principles, differentiation, finding when the slope is 0, and so forth. So, yeah, I would recommend, I can put a list of questions I would recommend doing to revise it, but it's up to you where you're going to concentrate your efforts. Somewhere around chapter 2, I reckon is a good idea. go.